doing some desktop sharing hopefully later on. We're going to do some MATLAB later on. So it won't capture that, but I'll make the MATLAB files that we develop in class available on the website. Okay, so you have to look at the MATLAB in real time, but it won't be recorded. The reason it doesn't capture things like desktop share and annotation and me moving the little cursor around like that is because were it to do so, file would simply get too big. It would have to actually do a physical video recording. As it is, it uses a very clever idea. It just basically records my voice, it records the slides, and it makes a note of where in time I went from one slide to another slide. So it just records my voice and a series of instructions as to when to go through the slides, basically. And also the chat, because the chat is pretty straightforward to record. So it records all that. It won't record video, unfortunately, because otherwise we're looking at gigabytes. Okay. But all the video stuff we'll be doing, it's not very much. It's pretty self-explanatory. We may be doing some MATLAB live in the class. You'll be able to see it in Maynooth. You'll be able to see it now live, but it won't be on the recording later on, if that makes sense. But I will put all the MATLAB files that we make in class will be available on the website. You can all play with them later on. Okay, so that makes everybody happy with that. We know where we are. So today we are going to do...
Sorry, Connor.
Hello, Palav.
I just follow here. I just missed last 2 minutes. I got disconnected. So this thing is recording. Is it we can view it offline? Is it? That's what you were telling, or?
And I was just explaining it's recording, but it doesn't record everything that we do. It records the voice. It records the slides. It records the chat. But it doesn't record things like annotations, like me moving around. And we're going to do some desktop sharing later on to do some MATLAB demos. That won't be recorded. It will be visible to anyone, but it won't be recorded.
That's fine, yeah. Thanks.
So today we are going to, I'm going to start doing these notes in sort of reverse order. You notice I've started with handout 7. So there's about 7 handouts we're going to get through. And I've decided to start with number 7 because in many ways it's a standalone. So we can do it very quickly, very easily. It doesn't depend on any of the other handouts, and it's really simple. There's about 100 slides in here, but only one of them is really all you need to do your assignment. So your job is to stay awake for the next 3 hours until you find that one slide that you need. Okay. But it's nice, and the nice thing about this handout is it's kind of fun. There's lots of nice things you can do with it. So it's a nice, gentle introduction to the world of computation and simulation, and you can do quite interesting and fun things with really small little bits of MATLAB code, as we'll see in class later on. We'll do some nice demos later on. Okay, so we're going to start with this handout. We'll see. It might take the whole class. It might take a little bit more. It might take a little bit less. I don't know. We'll see. This is a 3-hour lecture, about which I'm a bit nervous. I have to say, 3 hours talking for 3 hours. I've got family members that I wouldn't spend 3 hours with, to be honest. So 3 hours with a bunch of strangers, nice and all as you are. It sounds like a lot. So what we might do is we might break it up halfway through. If you see me just collapsing, I haven't had any lunch yet, so I'm liable to fall over. We might take a break about an hour and a half and go and have a cup of coffee and then come back. We'll see how it goes, okay? So that's okay. That's right, you need, I understand ECE students have a little bit of a flash. So what happens, you can leave at 4 if you wish, and then you can access the recording for the last hour. I don't think we'll go to 5. I think we'll go to maybe 4:30. So the last 30 minutes you'll be able to access online the recording. Or come up to me and talk to me, or we can talk on Monday. You can just look at the slides yourself. I mean, they're pretty self-explanatory. So I'm just explaining NUIN that some of our French students are very committed, and they've got actually 2 modules at the same time. That's how serious they are about their engineering. They've actually signed up for double classes, so they have to leave us about 4 o'clock. So that's okay. They can access the recording as well, hopefully later on. Okay. Good. Has anybody got any questions at this point about what we did on Tuesday? Tuesday was very easy. It was just me waffling, basically. This is going to be very.
Wouldn't mind actually. Can you go over it then? You know, I can sign up on that.
So Tuesday was very easy. It was just me waffling away about what the course was all about. Today is pretty easy as well. The level of mathematics we need in this is actually very, very minimal. We're going to do some more complicated mathematics in the other handouts, but this one is actually very easy, and you can do some nice things with, again, very simple integer division and some very simple mathematical concepts. Okay, so that's why I'm starting with it. It's a little bit fun, and it is easy. It's an easy introduction. So handout number 7, random number generation. So about, as we saw on Tuesday, life is random. We do not live in an orderly universe. Life is very, very complicated, and random things happen all the time. Okay? And that's what makes life very interesting, and that's what makes people write poetry and songs and great art. And we use it to make our life interesting. We gamble, and we bet on horses, and we play cards, and we embrace randomness as much as we can. So that's okay in everyday life. It's interesting. But for engineering, it's a little bit more complicated, because engineers have to get their head around randomness. Because if you're engineering some system or designing something, you have to really combat this randomness. You have to be able to ensure that whatever random fluctuations may happen in the system is still going to perform as specified. Okay? So randomness for engineers, we can't be as frivolous as poets, artists about randomness. It's a bit more of a concern to us. So we'll come to that in a second. The problem about randomness and probability and statistics in general, I think, is that they're quite troublesome concepts, because humans, by and large, think they understand probability, and they think they understand statistics. Your average person in the street thinks to have an intuition about numbers, and probability is beguilingly simple. Everybody can go in and play cards, and everybody can play the lotto, and consequently people have an opinion about statistics and probability that they don't have about vector calculus, for example. The average person on the street doesn't really care about vector calculus, but the average person on the street thinks they know a lot or a little about probability and statistics. And that little bit of knowledge is quite dangerous, with the potential for misunderstanding and downright bad behavior. You can play tricks, you can fool people all the time with misuse of statistics. It's a pretty serious area. So you've got to guard yourself and learn about statistics and probability, and learn about how little you know. Here's one of my favorite examples. I got this off a website the other day. Here are some statistics. Okay, I don't know, is the data valid? I don't know are these the actual data, but they're, they look as if they may well be true. I don't know how precise they are, where they came from, but certainly they tell a story that we're aware of. And what these data, this bar chart and chart is telling us is that, well, we all know the Internet Explorer used to be a very popular search engine. It was the only search engine for a good long period of time. And it has lost market share to, well, proper search, not search engines, but browsers, web browsers. It's lost market share to proper web browsers like Safari and Firefox, and ones that actually work over the last number of years. So you can see the green bars there is telling the sorry story of the Internet Explorer market share dropping over the years. The dots and the blue line are telling us something very interesting as well. It's telling us about the homicide rate in the United States over the last number of years as well. New York City, a few months ago, celebrated for the first time in, I think, 30 years, something really scary, 30 years, 20 years. And the first day in all of New York City, whatever that encompasses, the first day with nobody murdered in about 30 years, and we all get very happy about this. But by and large, that story has been mirrored throughout the United States in homicide rate. We put these two things together in the same graph, and we get very excited because we now understand the reason homicides are dropping in the United States. And this graph tells us very, very clearly that homicide rates are dropping in the United States because there is an obvious link between the use of Internet Explorer, which drives you slightly crazy because it's so bad, and getting into a murderous rage and going and killing people. This is quite obvious from this graph. This is the story. And this is the kind of stuff you will see. You guys are early 20s. In the next 50, 70 years of your hopefully long life, you will be bombarded with this kind of false use of statistics the whole time, because this is obviously not true. All somebody has done here is taken two probably correct statistical trends, superimposed them, and left it for the person watching it to infer a correlation, because that's what humans do really well. And one thing we're really good as humans is to look at data and try and thread a story to it. So your average person looking at this is going to look at it and try and understand it by means of a story or some simple, underlying cause. And a reasonable, not reasonable, but a typical cause or typical conclusion you might draw from this is that these are linked. Not only are they linked, they're linked in some kind of causal way. So in other words, one is causing the other. Okay? And there's no such causing. Maybe there is, but you certainly cannot conclude it from that. That is not. So a very important concept to bear in mind is that correlation does not imply causation. Two things can be correlated. Maybe these two things are correlated in some way. Maybe it is a third factor. Maybe the general economic growth in the standard in the United States.
I have it back now. All right, go on.
Okay, you're okay, guys. I'm going to mute a few people. So maybe there is some kind of third confounding factor. Maybe as with economic growth and rising prosperity, people feel less inclined to shoot each other and kill each other. And maybe with that growth in prosperity, people get more access to different kinds of computers and different kinds of web browsers. So maybe there is some sort of underlying link, but they're not. It isn't causal. It might be correlation, but it is not causal. It is not causing it. Okay, you will find many examples of this. There's lots of famous ones. For example, there's a very famous study linking ice cream to drowning. Ice cream is one of the most dangerous foodstuffs you can eat because there's a graph you can show like this showing the ice cream consumption in the United States and the number of deaths by drowning. And they link really. Why is that? Why is that the case? Anybody want to venture a guess why eating ice cream makes you more susceptible to drowning? It's a very dangerous foodstuff. Well, again, in that particular case, there's a third confounding factor. You eat ice cream because it's hot. It's a hot day. Okay, you don't eat ice cream in December. You eat ice cream in July. And in July, more people get into their pools to swim around. And if you go into your pool to swim around or into the sea, unfortunately, a small number of people will drown. So these two activities are linked to hot weather. Okay, so in hot weather, people eat more ice cream. And in hot weather, more people unfortunately drown. But you cannot conclude that it's the eating of the ice cream which is somehow making people forget how to swim. Okay. So stats, very important topic. You will be criminally bombarded with misuse statistics over the rest of your life. So as engineers, your job is to fight back and try and understand this. And be aware of it. Now, this is not a statistics course, so firstly, we are not going to get into this in a big way. This is a numerical methods course. Okay, so we're just going to learn a few tools today about how to model statistics and how to model uncertainty and how to model.
You are now muted. You are now unmuted.
Okay. Okay, anyway, I am. You seem okay. Okay. So that's just a warning. Go and take a probability course and learn about probability properly. I'm going to assume a certain knowledge of probability here today, but we're going to be focusing more on how to model the process. Okay? Good. So one of the things I gave you to do in your assignment, hopefully you've all download your assignment at this stage and have a read of it. Thank you to everybody who sent me information about their groups. I've been updating the website, been putting the groups up on the website. One of the assignments, hopefully you'll be able to download it and have a read of it, is to make a random number generator, which we will do today, okay? And use that random number generator to examine the so-called birthday paradox. So again, this is an example of seemingly counterintuitive results that can arise of humans' fuzzy notions about probability. And what this supposed paradox, it isn't a paradox, it just happens to be a fact. It's paradoxical in the sense that it comes as a surprise to people to hear the result, but it isn't necessarily a paradox. I'll mute some people here. Okay, anyway, apologies, I'm going to mute people occasionally if I'm getting stray noises coming in. So the birthday paradox isn't really a paradox, it's just a birthday surprise. It's just something that people are surprised by when they hear it. And what it is if you've got n people in a room, how large must n be? How many people must be in the room before two of them share a birthday together? Okay, so we all have birthdays. We discussed this on Tuesday. Everybody's got a birthday. two people in a room, you meet one one other person in a lift, chances are you don't have the same birthday. That would be a very big coincidence. Step into a lift with one other person who had the same birthday as you. Three people, it's kind of unlikely. You know? How many people must there be before there's a shared birthday in the group? And the interesting thing is most people, when they think about this, you ask people, studies have been done on this where they've tried to get a sense of your average person in the street, what they think of this. Most people would work along the basis of 365 days in a year to make the chances of there being a shared birthday more than 50%. I probably need more than 50% of 365 days, maybe about 180 people. So people work along that kind of line of reasoning and they say 180, maybe bring it down a bit, 150, maybe even 100. Turns out once there are 23 people in a room, the chances are that two of them have a shared birthday. It becomes more than 50%. Above 23 people in a room, it becomes higher than 50%. By the time you get to about 30 people in a room, it becomes, I think, about 90%. So this is a little bit counterintuitive. One would think the bigger numbers needed, but actually fact is not. So one of your assignments is to explore this in MATLAB, to make some random people in MATLAB and give them random birthdays. See how many of them you need before you get a match. So you still there, Manus? You okay? Send me a text. Can you hear me? Let's do a little experiment. Let's do the birthday paradox for the class. I need somebody to be a volunteer. And somebody get a blank sheet of paper from me. Blank sheet of paper? What blank sheet of paper? Good one. Volunteer. So what I'm going to do is, let's do it here. We have about 30 people here. We have about 15 or so over in Maynooth. So let's work out and see, do we have a shared birthday between this room and Maynooth and myself, okay? So let's kick off. Maynooth. If somebody in Maynooth, a single person, whatever person, pick someone at random. Ben, could you send me a text, tell me what your birthday is, Ben? Did you get a chance? Or anybody in Maynooth, send me a birthday. Oh, God, Ben's very quick. Ben had a birthday on the 17th of August. So we make under August, put down 17. Now, let's pick someone from DCU. When is your birthday? I have a birthday. 28th of October. Okay, so two people down. We don't have a match so far. Let's go back to NUIM. Let's pick Connor. Connor Flannery. When is your birthday, Connor? Connor has to think about this. Okay, Connor's not sure. Is he sure? Did the chat just come in? Good man, Connor. Connor had a birthday on the 24th of September. Okay, so we have three down and still no shared birthday. Right? This is where I get egg in my face. We end up with people who have their birthday. Good job, that's it. 29. Okay, 29. Okay, so what else? Maynooth, keep them coming, Maynooth. You can just send me text at random. I'll pick them out. Say Kieran Byrne. Hi, Kieran. Can you send me a text with your birthday if you get a chance? Meanwhile, Ian, you're up next. 13th of May. 13th of May and the 1st of February is Kieran Byrne and Maynooth. How was your birthday last week, Kieran? Happy birthday. Well done. Good man. Okay. Thanks. Okay, that's not bad. You're very polite. Next. 15th of March. Okay. There's still no matches. Anybody else in Maynooth want to volunteer? David Hurl, perhaps? David? Okay, a few more coming in from Maynooth. We got 24th of June. And we have the 23rd of September. That's close. How many people so far have we tried? 9. Okay, 9 people. We haven't had a match so far. Next, along here. 3rd of February. Happy birthday to you. That's close. One day off. Okay, so 3rd of February. A few more coming in from Maynooth. Ha Trin had a birthday on the 8th of September. James. James O'Neill has a birthday. What's the day today? 8th. James' birthday on Sunday, the 10th of February. Happy birthday to you, James. Okay, still no matches. Getting close, but no matches. Where will we go next? Anyone volunteer? 5th of March. You have that before? No. Okay. Anybody else in Maynooth? We'll keep on going here in DCU. You can throw me some more Maynooth whenever you get a chance. Next one. In June. Oh. Any more? 10th of December. There we got Saumya in Maynooth is the 15th of November. Number 1-5. Still no match. Not looking good. 22 of July. You had a July early on. Okay. Tension is mounting here, guys. We've got how many people now? 17. Oh my God. Next. 3rd of February. Oh, go. Okay, 3rd of February. Okay, there we go. So how many people is that? Okay, so after 18 people, so thank you to people in Maynooth. We had about 6 from Maynooth, or 12 from here. And we have found a match after 18 people of the 3rd of February, last, okay, my daughter's in the pub. So okay, so a match on the 3rd of February after 18 people. So if you do the sums, and we'll do the sums now in a second, just to have some points to all this rather than just talking about birthdays. Do the sums, we'll work out exactly how this works. It turns out that once you have 23 people in a room, the chances are 50%. So beyond 23, it becomes almost a certainty. And even here today, with just 18, we managed to get a shared birthday with only 18 people. Why is that? How can you think about this? Well, so how would we work this out? Well, rather than try to work out what the probability of 2 people in a room sharing a birthday, let's work out the complementary probability. Let's work out the probability that nobody shares a birthday. That's easier to work out. So we work out the complementary probability that no one shares a birthday. 1 minus that is at least 1 shared birthday. And that logic, okay? So there's 2 distinct sets here happening. There's either nobody shares a birthday or at least 1 shared birthday. That's 2 mutually exclusive events. Okay? So let's work out the probability of nobody sharing a birthday. Well, nobody shares a probability. So the first person has a birthday, second person, and first person has a birthday. The probability that the second person does not have the same birthday, well, he or she now has 364 days to choose from, because it can't be the birthday of the first person. So they've only got 364 days. So the probability of no sharing there is 364 over 365. The third person, in order not to have a birthday in common with the previous 2, now has 363 days to choose from out of 365. So the probability there is 363 over 365. So we can see, we can generalize this to n people. By the time we get to the nth person only has 365 minus n plus 1 days to choose from in order to not have a shared birthday. And the probability, therefore, that they don't have a shared birthday is this over 365. Okay, over 365. So this is the probability that there are no birthdays in common. And therefore, the probability that there is at least 1 shared birthday is 1 minus this. And it turns out if you do the sums, it's a very easy sum to do. You can do it in MATLAB, make a little code in MATLAB. And you can work this out very easy for different values of n. And what you find is if you put n equal to about 23, p becomes about 50%. And if you make n bigger than 23, p rapidly becomes heading towards 1995. It becomes a 7. In actual fact, the probability is a little bit bigger because this analysis here assumes that birthdays are independent. They fall independently, and they actually don't. They tend to clump a little bit at certain times of the year. Usually about 9 months after Ireland win the World Cup match, you often find a big spike in population, or a big spike in the birth rate. Not that happens anymore. But there are sort of events that can happen like that, and you do find birthdays clump as a consequence. Okay. That's that. Thank you. Is it Selmia, 15th of November. Thank you for that, Selmia. No, that came in a while ago. I got to acknowledge it. Okay, so that's a birthday paradox. So that's one of your assignments. You've got to make, in MATLAB, some kind of little bit of code that's going to simulate having n random people in a room, give them all a random birthday, and then keep track of what the birthdays are, and then work out whether there's a shared birthday. And do it loads of times, and work out therefore the probability of it happening. We only did it once. We didn't prove anything today, because this might be just an unusual classroom. You guys might be thinking, I don't know. So we didn't prove anything today. In order to prove it, in as much as you can prove anything in statistics, is you can do it many, many times and look at the overall performance, the overall stats as you do it 100 times or 1,000 times. Now, move on. Sort of people and probability and the way you can trick people and the games you can play. For engineers, it's a more serious matter. Probability or randomness can be either beneficial or problematic. So let's take an example. Radio engineers, of which I am one, have to contend with something called fading. And what fading is the following phenomenon. If you have a transmitter, say here, and you have a receiver here, and there are various ways in which energy can get from the transmitter to the receiver. One way it can go is just a direct path, straight from here, through the air, line of sight, or anything at the receiver. Okay? One way you can get energy to the receiver. In this particular very simplified two-dimensional geometry, you can also have a ray bouncing off the ground and arriving here. And the problem with that is the ray that takes the path along the ground has a slightly longer path to travel than the one going through space. And what that means is that it's at a phase. So this is a wave traveling this way, and it's a wave traveling by the alternate route. Both waves have phases. In other words, they're waves. They have peaks and troughs, and high values and low values. Okay? If they add in phase at the receiver, you get positive reinforcement. You get a larger signal at the receiver than you normally would. If they arrive out of phase, where one is high and one is low, they add together destructively, and you get negative reinforcement. You get a smaller power signal than you would normally get. In theory, you could get zero power if they are totally out of phase and the same amplitude. So this is a problem. This is a problem because when you're walking down the street with your phone, you're constantly getting these separate paths arising, and the waves are either constructively or destructively interfering. And occasionally, the signal you're receiving can drop to pretty much zero. And obviously, how can you have a conversation if you're not getting the energy in? This fading is a real problem for radio engineers, and there's lots and lots and lots of work being done to counteract it. Your phone is incredibly clever, and it's a very clever mitigation strategies it uses to counteract it. There's lots of very, very clever mathematical tricks and engineering tricks to solve it. And that's a problem. A beneficial aspect of this fading is that more recently engineers have decided to use this fading, this property, for secure communications. And the way to do that very simply is that for any given channel, and by channel I mean location of transmitter and location of receiver, the manner in which the signal fades, the precise form of the fading, the statistical variation is peculiar to that particular link in those two particular locations. Okay, if you move somewhere else, it has a different signature. Okay, so you can use it for secure communications because it means that you can verify that the person is who they say they are and are where they say they are. Because if somebody is trying to spook you and trying to send a communication from somewhere else, the fading in that channel will look differently. They'll have slightly different statistical variation, different statistical parameters, and you can tell that it is different than the desired one. You can say, no, I don't believe that you are who you say you are. Okay? So this can be beneficial as well. But mostly it's a problem. Mostly it's a problem. So how do you get around this problem? Well, you can use all manner of things. Sometimes you can use dual antennas. So if one is fading, another one is not fading, they haven't separated ever so slightly. So you might put two receivers in here. So if one is situated such that the two signals are destructively interfering and disappearing, the other one is a little bit separate, and the chances of him also destructively interfering at the same time is very small. So you can take the power from him instead of here. So that's called diversity. It's redundancy, basically. You put in more stuff than you need to do. Anyway, we needn't worry about that. But this is what you get. Here's a picture, two pictures. On the left-hand side here, we have, for the simple case we had in the previous page, the blue line here is the power, how the power would vary as the user moves away from the transmitter. So you see the power dropping. The blue line gets smaller and smaller and smaller, less power. But in a very simple fashion. That would just be line of sight. If there was no obstacle, if there was no interference, if it was maybe out in outer space and it was just pure line of sight. The signal would degrade, but it would degrade in a nice, simple fashion with distance, and you can work with that. The presence of the reflected field coming from the ground gives us the situation shown in the red curve. And the red curve here is the power you get when these only two rays, all it takes is two rays, a line of sight and a reflected add together. And you see these large dips occurring. These large dips are called fades. So at certain locations, as the person moves away from the transmitter, these rays are adding constructively or destructively, and you're getting quite catastrophic drops off in power of many, many dBs. Okay. This is a problem. This is what you get for the simple case. Over here on the right is an even more general case for an urban environment where rather than just having two rays, a line of sight and a single reflected ray, you've got many rays. Okay, maybe a line of sight or maybe not, depending on where you are, and then lots of different rays coming from different buildings, different roofs and cars and other people, etc. And this is how the field strength or the power varies for the user moving in two dimensions, moving this way along this axis or moving this way along the y-axis. And you can see a very chaotic picture here. Here's the power on this axis here, and the power changes very, very rapidly and very, very profoundly. Okay, you can have 30, 40 dB drops as you move half a meter. This is a really serious problem, which has been largely solved because we all have phones and they work. We should just acknowledge the fact that this is a hard problem to solve. Okay. So engineers would like to study randomness, but they don't want to have to go out with a phone and do hardware experiments the whole time. They like to be able to model it on a computer. It's very slow to have to go out into an environment, to a city environment, set up a transmitter, set up a receiver, walk around, and get kind of information. Very, very expensive to do this. So they'd like to be able to do it on a computer. They'd like to be able to model it in some way. Okay, so the challenge for engineers and for us in today's lecture is to work out ways to produce seemingly random results, maybe random fading or a random game of cards or something like that. Okay, but to do it without having to run an experiment, to be able to do it on a computer, but to do it in some systematic way. And the Monte Carlo method is the name given to a numerical technique for statistical simulations. It's used all the time in engineering and in physics. And it basically is a way of generating random sequences of random numbers. So it's like doing an experiment many, many times. So Monte Carlo simulation, like a Monte Carlo simulation where you take a virtual receiver in some sort of simulation and they can walk around the city and work out the power. Then you might do it again, and then you might do it again, and then you might do it again. And at the end of all these different simulations, you take all the data and then you can work out averages, standard deviations, and all that useful stuff. Okay? So Monte Carlo simulation is the name given. Strange name, given by John von Neumann. He was working in Los Alamos just after the war had ended, and they were doing statistical simulations. They just invented the atomic bomb, and they had decided it would be a good idea to now try and invent radiation shielding to prevent, to protect themselves from atomic bombs. So they were working on the problem of radiation shielding, and they needed to do some statistical modeling because the various materials they were using, the various atomic properties were statistical in nature, random in nature. So they needed some way of reproducing this randomness on a computer in the very early days of the computer. So he came up with this notion of making seemingly random numbers on a computer and then running experiments many, many times, generating random numbers in this way. Gave the name Monte Carlo, kind of slightly tongue-in-cheek, because one of his colleagues and his uncle was a bit of a gambler and used to gamble over in Monaco. The name Monte Carlo does actually refer to Monte Carlo in Monaco, the casino, chosen slightly tongue-in-cheek reasons. Now, it's used all the time. If you do a literature search in engineering, onto Google, the Monte Carlo method, you will find lots of technical papers, people using Monte Carlo techniques for simulating bit error rates in telecommunications. So in the example I just gave with the receiver walking around the environment with all this fading going on, how many bits is that user going to lose on average as they walk around? How many bits are going to be lost because of catastrophic power outages? So that's one way, one reason you could use it. Similarly, you might be looking at VLSI designs. You're designing some VLSI circuit, and there's small little uncertainties in the parameters. You've got a resistor, you've got a capacitor, you've got an inductor. They're never quite what they say. The resistance isn't quite what it says it is. The capacitance is plus or minus a little bit. And what is the net effect of all these small little imperfections in the stuff you're using? When you're trying to design a filter, for example, to do a very specific task, you can design it assuming that the inductor has such an inductance, the capacitor has such a capacitance. But if they don't, what if they're actually off by a little bit? What happens then? Well, then the filter will not work exactly as you think. What if there's a million of these little components and they're all off by a little bit? Maybe only one part in a million, but you know, it adds up when you've got many of them. And Monte Carlo techniques will do that. They take maybe again a circuit and add in a little bit of randomness to the parameters, and let's see what happens. Okay, so getting on to what we want to talk about. A random number generator is at the heart of a Monte Carlo simulation, because if you're going to use a computer to make many, many simulations in order to model VLSI design, the telecoms, you need some robust way to make numbers which are random. Okay, and this gets to the heart of the problem. So what's the problem we're going to address today? We're trying to create a sequence of independent random numbers with a specified distribution. That's the challenge. Ultimately, we would like to be able to make a sequence of numbers which have been taken from a certain distribution. Okay. So for example, the fading problem in telecommunications we saw there a while ago, the power levels that we would expect to see as the people move around in the city, they are random, as we saw. That graph on the right is very chaotic, but they fall within a certain distribution called a Rayleigh distribution. So it's not as if any value is equally likely. They tend to be clumps of preferred values and then tails. They tail away for very large values or very small values. Similarly here, here's a Gaussian distribution up in the top right-hand corner. Gaussian distribution, very common, used to model all manner of things. Probably the most commonly used distribution in physics and engineering. Okay. So our challenge is we would like to create a bunch of numbers that have the property to look as if they came from this kind of distribution. So if we're modeling a Gaussian distribution, we would like to produce a sequence of numbers. Most of them would be in and around here, in and around 0. That's where the bulk of the weight of this probability density function is, mostly in and around here, but occasionally numbers appearing over here or over here, and as the tail tails away to the right and to the left, sporadically getting numbers away over here, which you can see, are numbers over here, okay? So this is how we interpret this density function. We would expect to see the bulk of the numbers appearing around here, fewer appearing over here, and very rarely finding numbers over here. It's a challenge. Well, this is what I've just explained. Basically means loosely that every number that this thing is going to produce should be independent. It should not, you should not be able to guess what the next number in the sequence is based on the numbers to date. It should be a surprise what the next one is. So that's what independence means. And the chance of them falling within a certain range of numbers should mimic the density function or the distribution function of the desired function we're looking at. Now the distribution we'll be looking at in this course, we won't be doing Gaussian or Rayleigh, we'll stick to a uniform distribution. So a uniform distribution is a distribution where all numbers within that interval are equally likely. Okay? So they're all equally likely. In a Gaussian, some are more likely than others. In this one here, again, looking at the top right-hand corner, this graph, numbers in and around 0 are more likely, and the further away you go, the less likely. For a uniform distribution, we assume that everything is equally likely. Okay, so it's just a flat distribution. Okay. Now, some common misunderstandings about distributions and random numbers. Broadly speaking, if we were to make a random number generator which produced random digits between 0 and 9, if we do it well, any given digit, 3 or 4 or 5, will appear roughly 1/10 of the time. Roughly 1/10 of the time. Every pair of digits, 0, 1 or 3, 5 or 6, 4 or 9, 9, whatever possible pairs, 100 different pairs you could have, they will each occur about 1/100th of the time, roughly speaking. Okay? Because every individual digit is equally likely. There's 10 of them, 1 over 10, and therefore pairs of digits are about 1 in 100 likelihood. However, while that is the case, this is a trap people often fall into. If we take a truly random sequence of 1,000,000 digits, we would expect on average 1/10 of these digits to be, say, a 0, 1/10 of them to be a 1, 1/10 of them to be a 2, 1/10 of them to be a 9. But in actual fact, you will never get this occurring that neatly. So in a given sequence of 1,000,000 digits, you won't get exactly 100,000 zeros or 100,000 ones or 100,000 twos. You might have slightly more zeros, slightly less ones, slightly more twos, slightly less threes, etc. There's a statistical variation around. In the limit, on the average, if you do many of these sequences over and over and over and over again, the average frequency with which every digit occurs will tend towards 1 in 10. And I mean tend towards, in the limit. So as you take an infinite number of these sequences, it will eventually get towards 1 in 10. But for any given sequence that you create, you won't get 10% of them being 1, 10% of them being 2. Okay? And this causes great confusion, as we'll see in a second. Similar fallacies. So in the lotto, for example, you can spend lots of money on the lotto, and you can spend lots of money in buying books to tell you how to win the lotto. Okay? And one of the kind of things that people, the services that people provide lottery book writers, they look at the frequency with which certain numbers turn up. And they come up with pronouncements such as, well, this number hasn't come up for a while, it's due to come up. Because they have this sense of fairness that in a lotto 36 digits, each one should come up the same proportion of time, 1 in 36. So it's only fair that it should be 1 in 36 times 1 or 2 or 3 or whatever. And consequently they say, well, this one hasn't come up in a while, it's due to come up. You should pick this one, it's due to come up. And again, they're misunderstanding the fact that this notion of equally probable only happens in the long run, over 1,000,000 years, over 1,000,000,000 years. We'll all be dead by the time it evens out. The short-term fluctuations over our lifetime that will not be ironed out. If we keep on playing lotto for 1,000,000,000 years, it will probably even itself out. In any given lotto instance or any given week, and it is quite in any given week, it is anything can happen. Okay, so another misconception that people have about random number generation is that certain combinations or certain occurrences are more or less likely than others. So a big old argument you can have with people about the lotto is, so in the lotto, just for the benefit of our French students, here in Ireland we've got 36 numbers, you pick 6, or maybe it's been more, in my day it was 36. 36 numbers, you pick 6 every week, and if your 6 numbers come up, you can win several million euros. Okay? Like the Euro lotto. And people will argue with you, very vociferously, that some numbers are more likely, or some choices, some sequences are more likely than others. So for example, people will tell you, do not ever pick 1, 2, 3, 4, 5, 6 as your pick for lotto. It couldn't possibly come up. It's too ordered. It's too much structure in it. That's not a random sequence. The lotto always comes up at random numbers. This, to most people, doesn't look random. And what they're failing to understand is that this sequence is as likely as any other seemingly random sequence, 1, 5, 17, 32. As humans, we're imposing a meaning on this particular sequence. It makes sense to us. It doesn't make sense to the machine that does the lotto balls. The lotto balls, they come out randomly. we're imposing our own understanding of what that sequence means. We recognize it as being the first 4 integers, 1, 2, 3, 4, 5, 6, and we think it's special. It's not special. Okay? It's as likely as any other one to come up. There is an argument for, well, there's an argument for picking these 6 numbers, for your lotto numbers, on the basis that many superstitious people will not pick them. So if they do come up, probably less chance of having to share the lotto. But the flip side to that argument is there's lots of geeky people out there like myself who, out of pure badness, will probably pick these numbers, thinking that nobody else will pick them. So you could actually end up having to share the prize with 100 geeks. You know. So I don't know what the answer is. You can go and talk to Unpost and they'll tell you what the statistics are, whether this is a popular choice or not. Okay, but anyway, the purpose of that little anecdote is just that be very careful in how you interpret numbers and random numbers. Sometimes we think things look random and they're not, and we make demands of random numbers that are not fair demands to make. Similarly, this is the argument we just had a while ago. In an independent process, it is memoryless, so it does not remember. So if you have many sequences, you are doing 1,000,000 digits at random, and if the first 999,999 of those happen to be a 0, the chance that the next digit, the final digit, or that should say digit, not digital digit, is 0, remains at 1/10. Even though we've had an incredible string of 999,999 zeros in a row, the chances of the last one also being a 0 is still 1 in 10, assuming that it is a truly random situation, which in this case it probably isn't. But if it was truly random, if we were confident that it was a truly random situation, the fact that the first 999,000 have come up in this way, there is no relevance to the final go. The final go is completely independent. It does not retain memory. You click a coin, you get 9 heads in a row. The chance of the final head being a final toss being a head remains a half. It doesn't change if it is truly random. In this case, were this to happen, I think we could conclude that chances are it isn't random, or it isn't independent, there is something going on. But if it was working properly, if it was independent, and the fact is it would stay at 1/10. Okay. So we come to a problem now of how to make random numbers with computers. And this is what John von Neumann said about it. So John von Neumann basically kicked off this area. He gave the title Monte Carlo methods to this, the father of the modern computer in many ways, a very, very, very clever man. And he was one of the first people to generate supposedly random numbers using a computer. But he was smart enough to realize that there's a fundamental problem here in that proper randomness is random. You can't control it, so we call it random. Computers or any digital machine are not random. Okay, the last thing they are is random. Computers are very, very well engineered, they work very well, and they're not random. So how can we make something that appears random using an algorithm? Because an algorithm is not a random thing. Okay, so an algorithm is specifically designed to take an input and do a very definite sequence of instructions and then come up with a very definite output. Definite input in an algorithm. So how can we use an algorithm to make something random? So von Neumann realized this and he counseled against people who thought they were actually producing random numbers. You're not producing random numbers. What you're doing is something quite clever. Instead, you're producing numbers which are not random but appear to be random to anybody looking at it. Okay? Because the pattern that is there, inherent in it, in the algorithm, the pattern which is present, is so hard to spot, so well hidden, that to a casual observer it looks like a random process. They can't tell the difference. And that's the best you can achieve with a random number generator. You cannot make something truly random. You can make something that appears to be random and has nice characteristics that makes it from, say, a uniform random variable. So, desirable property. We'll look now in a few slides at how to do this. As I said before, the challenge in this lecture is to stay awake until we get to the one slide that tells you how to do your assignment. We're getting close to that slide now. So before then, let's look at what we would like. Before we see how to make random numbers on a computer, what would we like those random numbers to do? First of all, they like to be uncorrelated. And by uncorrelated, I mean that if you study the sequence of numbers that it has already produced, you should not have any information about what's going to happen in the future. They're uncorrelated. There's no information present to a casual observer in looking at the first sequence of output in determining what happens next. Okay? And we'll see some examples later on where this is not the case. Okay? So you've got to be careful. If you design a random number generator badly, this does not hold. Okay, long period. We would like, well, we will see now in a second, ideally the algorithm will produce a sequence of numbers that to a casual observer appear to be random. And ideally, that sequence of numbers will just go on forever and ever and ever and ever and ever. In practice, as we shall see, it repeats. Okay? So, if it's going to repeat, that's a problem because people can then see the pattern emerging. So what we would like to happen is that while it will repeat, it will take such a long time to repeat that for the casual observer, they will not be able to see the pattern emerging. So random numbers, or a string of numbers will be produced. Eventually they'll repeat, but not for a long time. What else would we like? We would like uniformity. If we were trying to model or trying to produce random numbers with, say, a uniform distribution, we would like that when you look at the output of this number, of the numbers that come out, that numbers would turn out uniformly distributed along the interval. So if we're trying to produce uniform numbers between 0 and 1, we would like not all of them to be close to 0.9 or not all of them to be close to 0.1. We would like a nice uniform spread. Subject to the caveat we saw earlier on, we cannot demand that it's perfectly uniform because no process is ever perfectly evenly distributed over all the outcomes. But by and large, we'd like to see some uniform distribution. And then finally, efficiency. If you are making designing a radiation shield like von Neumann was, or you're looking at telecommunications, you're doing lots and lots of computations. You're producing lots of these numbers in the order of maybe millions or billions. So it has to be computationally efficient. You don't want to have to wait half an hour for every new random number to come in. It has to be pretty quick. Okay. So we're going to move on. Before I move on, is anybody any questions how to do this? Hey Manuth, how are you getting on over there? If you have any questions, please send me a chat. Super duper. Eric Lawless is super duper in NUIM. Good man, Eric. Okay, thank you. Okay, no questions from NUIM. Let's move on. What we'll do is we're going to take a break maybe about 3:30. Okay, this is a 3-hour lecture. What I propose we do, we'll keep on going until maybe 3:20, 3:30. We'll break for maybe 10, 15 minutes and then start up a new session. That's okay. So do you hear that, Manuth? We're going to keep on going maybe till about 3:20, 3:25, and then maybe take a break for 10 minutes and then come back. Because we're not going to do 3 hours all at once because we'll just keel over, okay? David, presumably you're David Go. You're welcome to say, you're welcome to go. This is a 3-hour lecture because we're broadcasting to NUIM, so we take big long lectures. So feel free to stay, feel free to leave if you have to go, okay? Good. So all random number generators, or almost all of them, have a sequence of pseudo-random integers as their basis, okay? And so a typical random number generator produces random or pseudo-random integers. And then we can manipulate those integers to produce pseudo-random real numbers, okay? So it's a trivial thing to turn integers into real numbers. Okay, so we're going to present in terms of integers. And this is the basic idea of what we do. We come up with some sequence of numbers, sequence of integers, okay, many of them, and they're connected. So we start at any point within this cycle here, this big circle. And then the random number generator jumps from this integer to the next one. These are not necessarily in numerical order. This isn't, these don't go 1, 2, 3, etc. They sort of jump around. But the algorithm will, one of them, proceed to the next one, proceed to the next one, proceed to the next one, and so on, until it's exhausted all the way around, at which point it repeats. So the key to it is I've only got 12 shown in this particular circle. In practice, you'd have many, many millions or billions. So that's the idea. Random number cycle, in this case 12 integers, each dot is an integer. The nature of the cycle illustrates three things. There's a finite number of integers, again in practice maybe many million. And the sequence gets traversed in a particular order. So we can enter this sequence at any point, at any of these red dots, we can enter the sequence, but once we're in the sequence, we slavishly move to the next one, to the next one, to the next one, to the next one, until we go all the way around. Okay? And then we can see it's finite, there's a particular order to it, and then it repeats. Once you go all the way around, you're back to the start. So, this is what you've got to do. This is the slide you need to understand for your assessment. The most commonly used random or pseudo-random number generators, my apologies if I call them random number, I should be more careful and call them pseudo-random because that's all they are, they're pseudo-random. They're not actually random, they just appear to be random. The most commonly used one is a linear congruential generator, and this is a very simple thing to do. You can code one of these things up in MATLAB in about 4 or 5 lines, and we'll have a look at them later on. Okay, the following formula. We start off with x, some number x, and we update it. We start off with x0. Having got x0, we update it to x1, to x2, to x3, and so on. And the way we go from xn to xn plus 1 is as follows. We take xn, we take our present integer, we multiply it by some integer a, okay? To that, we add some other integer c, is this another integer? And then we do integer division. So we take this integer m, we ask the question, how many times can m divide into this sum, and what is the remainder? We keep the remainder. Okay, so this is integer division, and this here tells us divide m into this amount, an integer number of times. It will go into this an integer number of times, and there will be some remainder. Okay, so we'll do an example of that in a second. Where, some terminology, m is called a modulus. It's an integer satisfying m greater than 0. Okay, it's the thing we divide by. A is the multiplier, obviously enough, it's the thing which multiplies the previous number. C is the increment, again, obviously enough, it is the thing which increments this amount. Satisfies these conditions there. And x0 is the initial seed. We have to start this process somehow. We have to start it with a given integer value. And we call that x0 is the initial seed. We start off with x0. We do this process, we get x1. We feed x1 in here to get x2 and so on. So mod m means we take this amount here in the brackets, axn plus c. We divide it by m. There's some amount left over. That's the thing we keep. That's the remainder. So mod m means take the remainder left over after integer division by m. Now, in practical situations, if you're doing this for the practical implementation, you would take a very large number m, because remember this finite number cycle? M is the maximum number of integers you're going to get before it repeats. So in practice, you would choose a very, very large value of m, and we'll look at some good choices for m later on in the lecture, okay? In practice, we choose a very large value of m. In these notes, however, I'm going to use small values of m. Not very practical, but just in terms of explicitly showing how it works, okay? Not to be recommended, but just good for illustrating what's going on. Some more terminology. In the case of c equals 0, it's called a multiplicative congruential random number generator, because all we're doing at every step is multiplying if c is equal to 0. If c is not equal to 0, the terminology is that it's called a mixed congruential random number generator. Okay. Multiplicative ones are faster, if we're really getting down to the nitty-gritty, because there's one less operation, so it's a little bit quicker every time. So if speed is a real concern of yours, and multiplicative LCG is a little bit better, and they're adequate to good for many applications. In terms of the quality of pseudo-randomness you get, and we'll discuss those kind of qualitative issues later on, multiplicative ones are not as good as mixed ones, but they're not bad. and they're faster. So why do we do this? The modulo operation, what's the point of this? Well, it produces the appearance of randomness. Because as we'll see in the example now in a second, when you start doing this integer division, the remainder tends to jump around. Okay, it could be anywhere in the interval 0 to n minus 1. Okay, if you do it properly. Jumps around, and by jumping around, it gives the appearance of randomness, numbers which are randomly occurring. They're not randomly occurring. We know that, we've coded this, but to an observer, they look as if they are randomly occurring. A nice thing about these LCGs is that xn plus 1, the new pseudo-random number, depends only on the previous number, xn. You don't have to store all of them. There's other methods you can use. We're not going to cover them in lectures, where you use all the previous ones. And those ones have advantages because they can be better quality in terms of the randomness. They can be a better fit to a particular distribution. They've got some nice properties, but in terms of efficiency, they're a bit hard work because you've got to store all the previous numbers, and it's slower. Isn't it? Okay. However, this use of this modulo operation imposes restrictions because if we do this computation modulo m, the remainder is always between 0 and n minus 1. So hence, we're going to get this finite period. We can only get numbers within a certain range. The longest possible period we can get is m. After m, it has to start repeating again, okay? Because there's only m possible remainders when we divide by m. Okay, a little bit more terminology. One of these yolks we refer to as LCG, and then we just list the particular numbers, the multiplier, the increment, the modulus, the initial seed in this fashion. So we'll do an example in a second of how this works. Another quick observation is that the method as described there is going to produce numbers between 0 and n minus 1, integer values, 0, 1, 2, 3, 4, 5, up to n minus 1. For many applications, you don't want random integers, you might want random real numbers. Perhaps you're trying to make a virtual population of athletes or people, whatever it might be, and you're trying to assign random heights to them according to some distribution, Gaussian distribution. People are not one of integer value heights. You're not either 0 meters or 1 meter or 2 meters or somewhere in between. You're a real value quantity. So how can you use this process to get real valued numbers well easily? You can take the output, which is an integer between 0 and m. You can divide by m. That's going to give you a real number between 0 and 1. Simple way to do it. Or you can divide by m minus 1. The difference between the two approaches is that in the first case, if you divide by m, well, xn can never be equal to m. It's always going to be up as far as m minus 1 maximum. So this will never be equal to 1. The top one will never be equal to 1. So you'll only get real numbers between 0 and 1. So the round bracket here means that 1 is not included. You will not get the value 1 appearing. You will get the 0 included, hence the square bracket, but this can never be 1. If instead it's important to you that potentially you might get the real value 1, then you divide by m minus 1, because then if xn is equal to m minus 1, this will become equal to 1. Now in practice, n is so large, there's very little difference between these two. It's a small little stylistic. Okay. So this is going to give you real valued numbers between 0 and 1, either including or not including 1. And then to get more general real value numbers, you can scale that, or you can shift it, you can take away something or whatever. So you could take this and multiply it by 2. If you wanted to produce heights of people, for example, very few people bigger than 2 meters, I would have thought. So you can take the output here and multiply it by 2. That will give you numbers between 0 and 2, or whatever scale you want. So desirable properties for a uniform distribution, we would like these real valued numbers to be between 0 and 1, but on average, the weighted average of them should be about a half, and equally likely down towards 0 as up towards 1. It's just realistic. So that's how you do it. The little algorithm I showed about 2 or 3 slides ago, you can code that up in MATLAB in 3 lines, 4 lines. Very, very easy. The hard part is, and what you guys as engineers in this course have to wrestle with, it's one thing to know how to implement this. It's very easy to implement. The hard part, and the rest of the lecture is going to look at good choices for these values. You can stick in numbers, AC, M, X0, you'll get output. The question as an engineer is to try and look and try and work out, well, what constitutes a good LCG rather than a bad LCG. Let's do an example. Choice of multiplier A has a big effect on the period length and on the randomness. This is shown an example. Let's take an LCG. Let's choose the modulus equals 13. So we'll do remainder with respect to 13. We'll set the increment equal to 0. So it's a multiplicative LCG. We'll vary A. We'll do it for various values of A and see what effect that has. And we'll take an initial seed 1. Okay, so our first pseudo-random number is 1. Our modulus is 13. Our increment is 0. And we're going to try for various values of A. See what happens. So first of all, just so we all understand how this works, let's choose A is equal to 4 as a start. A is equal to 4. This is the process we're going to do. The next integer will be 4 times the previous integer plus the increment, which is 0, mod 13. In other words, 4xn mod 13. So the first number we're going to get is 4 times the seed, 4 times 1, which is 4. You can divide 13 into 4 0 times with a remainder 4. So our next random number is 4. Then the next random number takes 4, multiplies it by 4 to get 16. 16 mod 13, well, you can divide 13 into 16 once with 3 left over. Okay, so our next random number is 3. It's the remainder, 3. We feed 3 in here, we get 4 times 3 is 12. We can divide 13 into 12 0 times with 12 left over, so our next number is 12, and so on. We feed 12 in here, we get 4 times 12 is 48. We can divide 13 into 48 3 times, 3 13s are 39, with 9 left over. So our next number is 9, and so on and so forth. 4 9s is 36, 2 13s is 26, remainder 10, and then here's the interesting one, 20, 4 times 10 is 40, and you can divide 13 into 43 times with 1 left over. Our next number is 1. So what's happened now? What's going to happen after this? It's going to loop. Because our very first number, our seed was 1 up here. And in applying this with the choice A is equal to 4, our pseudo-random number sequence was 1, 4, 3, 12, 9, 10, back to 1. We keep on going. It's just going to go 4, 3, 12, 9, 10, 1, 4, 3, 12, 9, 10, 1 over and over again. Okay? So for this particular choice, and again I've deliberately taken a small value of m so we can explicitly do this, the maximum period we could have got was 13 before it looped. Here we got a period of 1, 2, 3, 4, 5, 6. 6 numbers. Okay? So this is not a particularly good choice for a random number generator. It doesn't have as big a period as we would like. We'd like the period to be as good as possible, so it doesn't begin to repeat. Okay, let's see what happens. I'm not going to do these exhaustively, but this is for an exercise for yourself, for your understanding. We just did this explicitly for A is equal to 4, so in the left-hand column here we have all different values of A from 0 to 12. We looked explicitly at A equals 4 and we saw that the sequence was 1, 4, 3, 12, 9, 10, 1, 4, 3, so on, with a period of 6. As an experiment for yourself, work your way through this and convince yourself that by choosing A is equal to 0, we get a terribly boring sequence, 0. With A equals 1, we get a terribly boring sequence, 1, because we just take the initial seed multiplied by 1. There's no increment, so it stays at 1 the whole time. 2 is a good choice. Well, up to a point, 2 is a good choice, because with 2, our initial guess is 1, we double it to get 2, we double it to get 4, we double it to get 8, we double it to get 16, 16 mod 13 is 3, so we get 1, 2, 4, 8, 3, 6, 12, and so on like this. And we get full period, we get 12, or not quite full period, m minus 1, 12. This is as big as you're going to get. Okay. So this is a reasonable choice, except that the numbers are slightly not as random as we would like. 1, 2, 4, they're just doubling every time. There's a lot of structure there. Okay, so this is not a particularly useful random number generator. So for 3, 4, 6, I'll let you work it out yourself. 6 and 7 also give you the maximum period. 12, okay, a bit more randomness, and then 8, 9, 10, 11, 12. Okay. People understand this chart, yeah? We have an LCG, we've specified C, we've specified M, we've specified the initial seed, and by varying the multiplier A, you get different performances of the random number generator. Okay. Okay. I propose we take a break. After the break, we'll do a MATLAB example. We talked on Tuesday about the problem that the iPod had with its shuffle algorithm and people giving out that it wasn't sufficiently random, whatever they knew. So after the break, we'll write a little bit of MATLAB code to make our own random music generator. Okay, I've got some music tracks, and we'll write a little bit of code to randomly shuffle through them. Okay, and we're going to have a contest, Manuth. Okay, you hear me, Manuth? We're going to have a contest, DCU versus NUIM, to see who can recognize the most random music tracks. Okay, so that'll keep you awake for the last hour. So I'm going to propose we take a break until 15:30. That's about 15 minutes. Go to the bathroom, get a cup of tea, do whatever you want, and then we will start again at 15:30. So the NUIM people, can I ask that you log out? Because I want to make sure that this gets recorded, and then I will make a new session at 15:30. Okay, so if you can log out now, and then at 15:30 you can log back in again, okay? Thank you. Sure, and maybe send an email if that's easier, because I need to. Okay. Let me just. Yeah, just send me an email. Sure. Sorry, just 1 second, sorry. There is a sort of neuro. 1, 2, 4, 8. Yeah. No. That. Oh, I see. Yeah. It's 1, 2, 4, and there is 1, 2, 4. 1, 2, 4. This one is 111, and you can find it here. Ah, yes, backwards. 111, 5, 3, 7. Yes, you get that kind of structure. Again, this is not a particularly good one because it's only any but you can get that sort of mirroring because depending which area you use, complementary choices of A. You can traverse it one way, and another choice of A will go to yeah. So that can happen. And I didn't really. Yeah, it's not random to do that. Person that makes, person who uses it. And other system which creates random. You can do that, yeah. That and you check yourself. Yeah. The problem there is that's a good idea. However, is it more random to everything random? Oh, yeah, I understand the question. Our job is complicated because we want to ensure that it is random, or it appears random, but also, remember, it also has to be independent, and it has to be, in our case, we hope to be uniform. So with the kind of thing that you're suggesting, sometimes you can affect those other properties. So you can try it and see. It's a good idea. You can try it and see. What you need to ensure is that when you do that, it doesn't affect the air quality. Every result in the from the solution. Again, I mean, you can experiment with going into other circles, but you just have to be perfect because there's a lot of theory, and you'll see later on in choosing these circles properly. If you change it to other circles, it can affect the policy of the random generator because it no longer you have to be a little bit careful about that. You can make it more random, but it may no longer be a uniform random. It may become some other kind of distribution, you know?
You have been kicked.
Which is the 365 minus 9. N can go from 0 to n goes from 1 to another. There's 2 people in the room, and as equals 2. Probability of the ratio of the fate is 1 multiplied by. This is the case for n equals 2. So you take 265, you take away n, 2, and you add it. Okay, so n is the number of people in the room. Random number stuff. Get that out of the way, okay? You don't have to do the questions in order, do the questions whatever order you want to do yourself. So if you want to have a go at the other ones, by all means, I can give you some notes and you can read up and see what you want to do. But it makes more sense to start off with the random number generator questions and get that done. Okay. So, Manus, you can hear me, great. So what we're going to do in this, we're going to make a little MATLAB file, or I've made a little MATLAB file. We're going to explain it and look at it and try and understand how it works, okay? And the particular MATLAB file is a random music player. And then we're going to have a little contest. We're going to have NUIM versus DCU versus me in terms of recognizing music, okay? So we'll explain the rules of that in a second. So what I've done is, hopefully, just going to mute some people. Okay, so I made a, what do we call it? I made an M file earlier on today. Music quiz, I think it was. Also, at the start, I've got to change the. God bless you. Let's try again. Understanding here. Now, so what I have up on the screen, Manus and DCU, is a piece of MATLAB code I wrote earlier on. What I did was I took 32 songs and I took a little 10-second snippet from 32 songs. Okay, so I spend my 10-second snippet from 32 songs. I made 32 WAV files which I've put in a folder, and I've now made a little random music player which we're going to see if it works. Okay, so let's work our way through this M file. You can see the M file. Send me a text in Manus if you're having any trouble with any of this. Hope it works. So the first thing we do in our M file is just for make things nice and neat. Good practice when you're making an M file to maybe start off with something like clear all, because you might have been working on MATLAB for a while. There might be variables in the system. You want to just flush everything and start again. So clear all just resets everything, okay? Close all closes all windows. Perhaps you've been using MATLAB for a while, there's windows open, etc. We're I'm going to close all those windows. This particular thing doesn't open any windows, so it shouldn't be a problem. But again, good practice to do that. CLC is a nice thing. It brings the cursor back up to the top of the workspace. Some people find that kind of neat. Okay. So first thing we do is we specify our random number generator. So these 4 lines here are the 4 numbers we're going to use for a random number generator. So in the lectures earlier on, we saw we can make a linear congruential random number generator with 4 numbers. A is the multiplier, C is the increment, M is the modulus. I'm going to divide things by M, get the remainder, and X is the initial seed here, where it's going to start off. So this hopefully makes a cycle of 32 numbers that get traversed in a seemingly random way. And we're going to jump in with our first number is number 3, okay? And then it'll update according to the process we saw before, okay? I have it set for 32 turns. I don't think we'll get 32 turns done. We'll do a few and see if it works. Okay, that's just a variable to see how many goes of this pop quiz we want to do, how many turns. It's set for 32. And then very simple, a for loop. So we're going to have a little thing called counter, and we're going to, for counter, or for CT, equals 1 colon number of turns. So this is going to make a little variable called count. It'll start off at 1. It will do all the instructions in here. And then when it gets to end, it will go back in again, and CT will be equal to 2 and 3 and so on. It's a for loop. You know what a for loop is. Until it gets to number of turns, which we've set as being 32. Okay. So every time we get into this little loop here, we're going to update our pseudo-random number. So how do we do that? Our previous number was X, which has been initialized to 3 up here. Okay. What we do is we take our previous number, we multiply it by A, which has been specified up above. We add the increment C, which has been specified up above. We ask MATLAB to work out the modulus of this quantity here, AX plus C, with respect to M. So in other words, divide AX plus C by M, integer division, see what's left over. What is left over becomes the new value of X. And what's nice about it here, we see we just overwrite the old value, which occurs here, the new value. We don't have to make a separate, we don't have to store all the numbers. We could if we wanted to. You can make an array and store all the numbers if you so wish, but this is more efficient. We just overwrite the random number with the new version. So this gives us a number. It's going to give us a number between 0 and m minus 1. Okay, 0 and m minus 1. And were we to end the loop there, that is your random number generator. That's all it takes, 7 lines of code. Very easy to do. So a little bit of extra MATLAB know-how. It's kind of similar to C syntax in some ways, so it might be useful for you to see this kind of stuff. In order to do something a bit more nice and to manipulate a little bit of multimedia, we say we use a function called int to string. So what we say is S is now a string, and it takes the integer X, which has been defined by our process, and it converts it into a string. It's a different kind of data structure. It's now a string, so it might be 1 or 2 or 5 or whatever, but MATLAB will interpret it as a string. And then we tell MATLAB what song to play. We say song is string concatenation. That's what strcat means, string concatenation. And I have off this desktop folder, I've made a folder called snippets, and I've put my 32 WAV files in there. So we make a file, /snippets/track. We concatenate S, which is the number, 0 or 1 or 2 or 3 or 4, whatever it might be. Concatenate that, and then we concatenate .wav at the end. So this is going to produce a string which will say ./snippets/track 1.wav or track 2.wav or track 3.wav, whatever it is. Then we tell MATLAB to read in the WAV. WAV read, again another MATLAB inbuilt function. It reads in this file. It interprets it as a 2-dimensional array, just a sequence of numbers with the samples in it. So Y just becomes a big 2D matrix with all the values. Important to put a semicolon there, because if you didn't put a semicolon there, it's going to spew them all out to the screen, and that's going to slow things up. We then, just a little bit of output, so we know what's happening. It's fprint1 playing song X. So X is a number between 0 and 31, so just to tell us which one it is. And that way, we can check. it's working well. We can do the sum ourselves and guess what the next number is going to be. It'll then take Y, and sound is an instruction to MATLAB to play that WAV file, or that structure Y which contains the WAV file, play it at 44,100 samples per second. You've got to specify this. If you get this wrong, it sounds really cool. It plays too slow, it plays too fast. Kind of ambient, that kind of stuff. But these were sampled at 44.1 kilohertz. So we put in 44 kilohertz. We pause it, or we say press any key to continue, and then we pause. We have to pause because if we didn't pause, it would just happen very, very quickly, and MATLAB would get confused. It would load up all the files immediately and try and play them all immediately, and I did that actually. So I forgot to put in pause, and my laptop crashed. The pause is important. Okay, so you got to put in pause. Okay, so this is so people understand what's going to happen here. I'm going to run it. What's going to happen is it's going to join this. At x equals 3 in the cycle between 0 and 31. It'll play that. Actually, it won't. It'll update that to get a new random number. It'll play that associated random piece of music, and then when we press to go again, it will go again. Okay. So, Manuth, did you understand all that? Manuth, are you still alive? Anyone alive in Manuth? Yes, still alive. Good to hear. So what we're going to do is we're going to have a little competition. Me against DCU against NUIM, and the rules are as follows. I will play a piece of music according to this, 10 seconds. First, NUIM have to text me, chat me with the artist and the song. Okay. Then at that stage, DCU will tell me who the artist and the song is. You do it afterwards, because if you say it, they'll hear you. So, NUIM go first. They text me the answer. You tell me the answer. If you get the artist right, you get a point. If you get the song right, you get a point. If none of you, between the combined intellectual weight of DCU and Manuth, can't get the artist, I get a point. And if you can't get the song, I get a point. Okay. That's here we go. Very exciting for a Friday afternoon. Let's see, is this going to work? I have speakers. Hopefully it works now. I haven't tried it with the speakers, but I tried it earlier on. I think it. So, what we need an initial seed. So let's start somewhere else. Let's start. Give me a number between 0 and 31. I heard 15 in the middle of all that. So, yes. Kira says 8 for some reason. Oh, thank you, Kira. Kira was suggesting a number. Thank you. 8. Thanks, Kira. Okay, now this little asterisk here means I haven't saved this, and that's something else I did earlier on. I didn't save it, and then I tried to play all the music at once, and my laptop fell over. So, music quiz. Let's see what happens. Anyway, shot. Keep score. This one. The Ian's turn to keep score. 2 columns. DCU, NUIM. Okay, you know the rules. Okay, so NUIM, you know the rules. We need an artist and we need a song title. So while they're doing that, we started off with our initial seed was at 15. And then we played song 12. So how did that happen? Well, 15 multiplied by, what was A? A was 5, wasn't it? 15 by 12 is 60. No. What was our seed? 15 by 5 is 75. And 75 divided by 32 is 64. How do I add 1 to it? He was 1. Very good. Thank you. Give yourself a point. Okay, so NUIM have an answer in. So DC, who is that? Is Buddy Holly, Oliver's Army on the other? And this is Costello. Okay. All right, Elvis Costello, Oliver's Army. So 2 points to DCU, 2 points to NUIM, and 0 to me. Okay, it's been a long day. Okay, playing song 12. What would be the next song we just played? What's 12 by? What was I thinking? 560 plus 1 is 61, and the seed is 32. I reckon 29. It should be 29 now. Okay, anyway, I'm ready. Okay. Oh, you're getting a disturbing view into my record collection, by the way. And an unwelcome aspect to all this. Okay, so anyway, you know the score. Artist and track, and then DCU as well. Don't say yet. Ooh, not sure. Do you want to consider that? Not so sure anyway. I'm almost there. Okay, fair enough. Good man. Okay, DCU, who's that? Is he top? Yeah, who was the song? That was man, very good. Excellent. Okay, another 2 points for everyone and 0 points for me. Okay, this is... Okay, so playing song 29, where are we going to go next? 29 by 5 is... 145, isn't it? Plus 1 is 146. What's 146 mod 32? You guys are young, you should be able to do this. 32 by 32, 64, 128. 8, is it? 129, 145, 146. I reckon 18. What's the next number anyway I'm going to be? We're too tired over here to do it. What's the next? If we just played track number 29, we're trying to work out what's the next number going to be. 18. Okay, we reckon 18. Let's see. We right.
Love is a burning flame.
Actually. Okay. This is too easy. Good woman, Maeve. Okay, DCU. Who was that? What's the song? A little too easy. Let me get a hard one. Okay. Okay, anyway, who's that? Okay, I think we all know the song. It's got to be the who sang it though. So anyway, yeah, you're too smart. Just spell it right though, for God's sake. I like Maeve's take on the artist. Maeve reckons the artist was Shrek. He's very good. Good woman, Maeve. Okay, DCU, who is that? Jeff Buckley and? Can you spell hallelujah? Okay, they can't spell hallelujah here either, so it's okay. Maeve can spell it. Good woman, Maeve. Okay, it must be, I put in 1 or 2 hard ones, so this is, what's the next number going to be? 27 by 5 is 135, plus 136, should be 8, shouldn't it? 8. Okay, anyway, okay, we got conflicting answers from NUIM. Okay. Connor's cracking the whip over in NUIM. Good man, Connor, you're right. Okay, DC, who was that? This dish. Okay, 2 points for everybody, none for me. Okay, we're not going to do all 32 of these, by the way, because much as I would like to, I don't have to get paid to sit down and listen to music with you guys, which would be nice, but you can't. So we'll do a few more. You can wrap it in a cloak of education by continuing to work out what the next number is going to be, and you can justify it, okay? So the next number is going to be what? Somebody tell me what the next... NUIM, what's the number going to be? If we're at 8 at the moment, what's the next number going to be? Have you learned anything in Maynooth? Or what you reckon? 9. 8 plus 5 is 40, plus 1 is 41. Mod 32 should be 9. Okay. We just don't care what the next number is. They just want the music. Okay. Okay, we're not. Ah, Eric Lawless, good man. Okay, we haven't met Eric Lawless yet. He's in Maynooth. He's obviously a pretty classy guy because he respect Eric Lawless. Or they got Shazam. I can't believe they got Shazam out. And just to get Shazam. DCU, anyway, I'm have it right. DCU, who's a composer? It is Beethoven. That's good. Yeah, 30s. Good stuff. Okay. Irish students, hang your heads in shame. We had to rely on the cultured French students for that one. The Irish students wouldn't even make eye contact that time anyway, and they're always Jesus. We've gone some Black Sabbath. Okay, we'll do 2 more because we have to get a winner. It isn't going to be me, so it's tied at the moment. So we'll keep on going until we get a winner. Okay. Okay, that was very easy. Very good. Okay, TCU. Okay, one more. Keep on going. Oh, this could be the one. Okay, I need and what's the artist? What's the artist NUIM? Oh, they're good. DCU. 65, very good track. I'm not sure about the track over here. NUIM, I think, might have won. One more chance now. There's a random lyric generator here. Okay, the track is "I Want You Back." And okay. I don't understand anything anyway. I'm not writing anymore. Okay, so 1 point for DCU, 2 for NUIM. So NUIM win. DCU come second. I come in with 0 points. Not perfect. I thought maybe the classical ones might show you. So fair enough. Okay, anyway, you're the winners. Well done. So let's crank this open again. So, so that's an example of something relatively. Oh, you guys got to go. So that's an example of something relatively complex you can do with how many lines of code? 21 lines of code, okay? So guys, this is the French students are double booked. They got to go to another lecture, okay? So we'll keep on going for another half an hour or so until we get these finished. So that's an example of a pretty relatively sophisticated piece of code you can write with 27 lines of code. So just give it a minute until these guys are gone, okay? Yeah, the song is called, the file is called song. tell you now. So let's just go through the code again quickly. There's a question just about some of the formatting here. So the first 4 lines here are our random number generator. So had we started with a different seed, what was the first time we heard there today? Is answers, whatever it was, Oliver's Army. Had we come in with another seed, what would have happened was we would have entered those 31 songs at another point, okay? And we would have gone to the next ones from there. Okay? We started off once we hit 15, we were obliged to go through that sequence from then on. You didn't know what was going to be next. I didn't either. I don't know what the tracks are, but in theory I could have known what was coming next. To you guys it appears random. Okay, so those are 4 numbers. So the question was here, S. So what we've done is we made a number, an integer, using this x is equal to mod ax plus cm. We've turned that into a string, so MATLAB can recognize it as a string of characters. And then we've asked MATLAB to make another string. We've concatenated 3 strings together, and this is just the address of a file relative to this directory. So it's /snippet, so it's a folder called snippets. We're in the desktop, so snippets is a folder on the desktop, and it tells MATLAB to make this string called snippets track whatever it is .wav, and then so this is a direction to a file. And then your question was, what did wavread do? Wavread reads in whatever is in that file. So song is a file. It's a string which tells MATLAB points to a file, and then wavread reads in everything in that file and turns it into an array Y. And then sound plays that particular array Y. And there we go. Okay, answer your question. I don't really know how it works. I mean, it's something that MATLAB, it's hydraulic. I mean, you can go and I think in most MATLAB files like wavread and sound, you can go and find them. You can find the actual .m files themselves and go and have a look and see exactly what they do. So it's sort of hidden from us here, but if you want to look further, you better find it. Okay, so that was that. So for your assignment, you've got to do something similar. And for your assignment, I would not suggest using this LCG. It's not a very good one. It's too small. 32, maximum cycle 32 is fine for having a bit of fun with some songs, but it isn't big enough to do the kind of stuff you need to do. So what we're going to do is go back to our slides, and we're going to talk about, we're going to go back to our slides and have a quick chat about what makes a good choice of LCG. So we did our little experiment. Where we go here. So another thing to notice about LCGs, as we've seen for a full period LCG, and that one was, it would cycle through 0 to 31. Okay, this gives us 32 distinct possibilities. Choosing a different initial seed just kicks us off somewhere within that cycle. Okay, it shifts the starting point. So you go through everything in the same way. So the actual length of the period is determined by A, C, and M. These numbers here. So for a full-length period LCG, choosing a different initial seed doesn't change anything. So for example, LCG, where A is equal to 6, 0 increment, mod 13, and initial seed x0 is a full-length generator. We start off with x0 equals 1. We get this particular sequence. You can verify that for yourself at home. If instead x0 is equal to any integer between 1 and 12, it wouldn't affect the apparent randomness. All that would happen is we would jump in at a different point in this sequence, okay, and just traverse it from then onwards. However, if it isn't a full-length period generator, so if the choice of A and C and M are such that we're not going to get a full period of M minus 1, the choice of the initial seed is quite important, because some can give you longer periods. So for example, here's LCG 3016X0, and in this case we see that the choice of X0 is quite important, because It isn't a full length period generator. The best we can get is period 4. Get is period 4, and that is achieved if we have an initial seed equal to 1, 3, 9, or 11, or indeed 5, 7, 13, or 15. And these give us these particular sequences, both of whom are period 4. They're different sequences though. This goes 1, 3, 9, 11. This goes 5, 15, 13, 7. Both are going to repeat after that. So they're distinct sequences, but both are period 4. Other choices of X0, not such good performance, 2, 2, 2, 1, 1, etc. Okay? So this is obviously very important. If you're trying to make a random number generator, you want as many possible numbers as possible before it begins to repeat. Because once it begins to repeat, the results are no longer reliable. You're just replicating what you did before. Okay, so you're not getting any new information, any new statistics. So choice. So here's some bad choices, or not so good choices rather. When m is a power of 2, the 2 to the n, so 1 or 2 or 4 or 8 or 16, 32, etc., and c is non-zero, you can get maximum period, m, only if a mod 4 is equal to 1 and c is odd. So this explains in the code we just looked at, I picked 32 songs for a reason. I picked 32 songs because that's 2 to the power of 5, okay? So it's of this form. I picked c is equal to 1, so it was of this form, and I picked a to be 5. I picked a quite carefully because a mod 4 is equal to 1 with 5 mod 4 is equal to 1. This satisfies this conditions here, and it gives us a maximum period m. That's those numbers I chose for our MATLAB code were not chosen randomly. They were chosen with this in mind here. Okay? So here's some examples of this. LCG, we have m is equal to 2 to the 4, so it's of the form 2 to the n. And we have a mod 4 must equal 1, so we've chosen either 1 or 5 or 9 or 13 because all of these a's have 1 left over when divided by 4. We've chosen x0 equal to 1 in every case, and these are the sequences you get. Okay, you get full-length sequences of 15 digits or 16 digits, 0 to 15. Okay, so that looks pretty good. Any problems with that? So it looks superficially as if that is a good generator, albeit for a small number, 30, 16, but we could easily scale that up. But there's a problem with this kind of approach, and can you see what the problem is? So here we got 4 superficially reasonable looking sequences. They're full-length sequences, and they jump about a bit. First one isn't great, obviously, 1, 2, 3, 4, 5, 6, 7. It's not, not very random there, but the other ones seem to jump around much more. There's a problem with the last 3 that isn't immediately obvious. Can you see any structure? NUIM have a good answer for me. So Kieran Byrne, presumably. And Kieran has noticed that there are odd numbers. So for a is equal to 5, we've got odd number, even number, odd number, even number, odd number, even number, odd number, even number. For a is equal to 9, we've got odd number, even, odd number, even, odd number, even, odd number, even. And for a is equal to 13, odd number, even, odd number, even, odd number, even. Okay. So what we see is with any of these, they jump about a bit, but if someone were to study this, if you were trying to get some sort of security feature and use number generator for security code, it compromises slightly here because someone studying this would be able to see, well, look, every second number is odd, or every second number is even, and that gives them a little bit of information about what the next number is going to be. Just a little bit of information. It doesn't tell them what the next number is going to be, but it gives them a little bit of information. That's not good, because you don't want to give these people any information if you're trying to make a security. So this is an okay LCG. It's not great though. It's compromised by the fact that it alternates, as Kieran has pointed out, even and odd numbers. James has an observation. Every 4th sequence increments to the 5th by 1. Not quite sure what you mean by that, James. For a is equal to 5, every 4th. 4, 5. That's what you mean. Oh yeah, very good. Gotcha. Yeah. 4, 5, 12, 13, 14, 15. That's less of a problem because we're not looking for structure between different generators. We're looking for structure across a row within a generator. Okay. Oh, yeah. I got you. 8, 9, 4, 5. Yeah, gotcha. James, well done. You should be a code breaker. Well spotted. So what he's pointed out is that you got this sort of little pockets of structure happening, 8, 9, 4, 5, 12, 13. Again, that's of use to somebody trying to practice. They could look at this and say, well, not only is every second one odd and second one even, there's these little pockets of patterns turning up, and we can use that. So not ideal. Okay, so Ben has noticed something else. In the third row, the difference between all consecutive numbers is 1, 7, or 9. Okay, it might well be, Ben. Thank you. But let's move on because it's 10:04. So thank you. So what Ben and John and James and people here are pointing out is that there's all these little substructures and structures occurring in an LCD that it seems random, but to somebody intent and malice, they could look at it and they could they could maybe compromise it. Okay. So odd and even numbers. So in other words, the lower order bit we're going to flip between a 0 and a 1. Odd, even, 0, 1. It could bring us some binary 0 and 1. Okay, so that's not good. And then that's for the maximum period choice of A, 1, 5, 9, 13. Other choices, A is 3, A is 11, the period drops to 8. When A is equal to 7, it drops further. And then for these choices, 2, 4, 6, 8, 10, 12, the LCG will sputter along for a few numbers and then ultimately produce a constant stream. That's completely crap. Okay, so that's that's an OLCG, but it's kind of fatally compromised for these problems. And that may or may not be a problem, so depending on the application you use. I use it for a little quiz because it didn't really matter that every second one was odd or even in the quiz. But if there's some other situation where you're trying to maybe be secure, that would be an issue. Okay, other choices. Maybe if m is equal to 2 to the n, says before, so m is 1, 2, or 4, 8, etc. And we have a multiplicative LCG, so the increment is 0. The maximum period in this case, you can only achieve maximum period of m over 4. It's the best you're going to get. You're not going to get m minus 1, you're only going to get m over 4. And it's only obtained in certain cases if m mod 8 is 3 or if m mod 8 is 5, for example. And the initial seed must be odd. Okay. The lower order bits of this kind of LCGs are not random. Okay. It isn't quite a case of flipping odd and even, but there's still some structure. If we were to examine this sequence in a binary code, you'd see some little patterns and sequences emerging that could be exploited. Okay, so this is what you get for 3, 5, 11, 13. The best you get is 4 numbers before it starts to repeat. And you can see even between these 4, it's 1, 3, 9, 11, 5. So these numbers are the numbers that appear. So it's, again, compromised. So this is a really bad one. Okay, choice 3, this is a good choice. When the modulus m is a prime number and A is greater than 1, so the multiplicative factor is greater than 1, you can get maximum period of m minus 1, no matter whether C, the increment is 0 or not. Okay, and you can get this maximum period if and only if and only if is a fancy mathematical way of saying if this clause is satisfied, it implies what follows, or if what follows is satisfied, it implies backwards. So in other words, if this holds, A must be a primitive element modulo m, or if A is a primitive element modulo m, or this holds. What is a primitive element modulo m? That's a funny definition from group theory and finite field theory in mathematics, number theory. So if m is prime and A is a primitive, then A is a primitive element modulo m if and only if the following holds. A to the power of 1 or A to the 2 or A to the 3 or A up as far as m minus 2, modulus of m is never equal to 1. It's late in the Friday, let's take that slowly. We have a number m, we have a number A to the 1 mod m is not equal to 1. A squared mod m is not equal to 1. A cubed mod m is not equal to 1. All the way up as far as A to the power of m minus 2 mod m is not equal to 1. If that is the case, we say that A is a primitive element modulo m, or a primitive root. Okay, that's just a definition from number theory in mathematics. Okay? If that is the case with all this, you get a very good LCG. Okay, so if you can do this, you get a very good LCG generator with very good randomness and a very big cycle. Okay, you can make m very, very large. in this case, you can never get a period of m. When you ever get m minus 1, there's always one integer that will map to itself. Okay, so you shouldn't use it as an initial seed. It will just stay at the same number, never change it. Okay, so for example, we'll see that example later on. Even when c is non-zero, you can never quite get maximum period of m. You get m minus 1, but that's a typo because if m is a really big number, m minus 1 is still sufficiently big. Okay, some consequences of that. Okay, we should pick a greater than 1 to get some randomness. So here, for example, I talked about why do we never get period m? We only get ever m minus 1. It's because there's always one little integer you can't include in the sequence because he maps to himself. So for example, 6c13, this is of what we just discussed. M is prime, A is a primitive root modulo m. And we have, in this case, if c is equal to 0, increment 0, the number that maps to itself is 0. If c is equal to 1, the number that maps to itself is 5. If c in this is equal to 2, the number that maps to itself is 10. So for example, for c is equal to 2, and if the number is equal to 10, we get the next number will be 6 times 10 plus the increment, which is 2, which is 60 plus 2, 62. 62 mod 13 is 10. There's 4 13s is 52, 10 left over. 10 maps onto 10. There's always one number to beat that. So hence you can never get full period, only ever n minus 1. The best one to go for is, well, not the best one, but a recommended one is given by Park and Miller. You can read about it in this reference here. You can download the journal paper and have a read about it. And they suggest this LCG. A is equal to 16,807. M is equal to 21474836647, the phone number. And that happens to be 2 to the power of 31 minus 1. It's a prime number. It's a pretty big prime number. Okay. C is equal to 0. You don't need an increment for it. You get full period of m minus 1. So if you use this as a LCG, kick it off with a random seed, whatever you're going to get, you're going to jump into the middle of this cycle of numbers, and it will be 21474836646 numbers before you're out to the far end, before it's actually repeating. That's good enough for most purposes. Okay. The same initials. Okay, let's come back to that in a second. You might wonder where all this comes from. I'm sort of throwing these results out to you. Something I don't like doing is to give you results but don't explain where they come from. So why is the case, for example, that this holds? It's not obvious, and I don't expect it to be obvious. I don't expect you to look at that and say, oh yeah, obviously that's the case. And similarly for the other two choices we saw, we're going to twin choices. It isn't obvious as to why this is the case. There's a lot of number theory and we're in the School of Mathematics here in DCU at the moment. A lot of people working in mathematics would work on problems like this. People who are into number theory, group theory, their job is to look for prime numbers and look for these kind of relationships and prove these kind of results. Okay, and they don't just do it because they like doing it. I'm sure they do it because they like doing it. But you can see by finding out these kind of, solving these kind of theorems and producing these kind of results about prime numbers, we can produce practical things like number generators. So we're not going to get into all that theory, all that prime number theory. It's beyond this course, but suffice to say, it exists, and that's where all these results come from. I'm not just plucking them out of the air, okay? Okay, so we have a problem, a further problem, in that we did a little random music generator there, and if we kick it off with the same increment every time. So say you've written a piece of code, okay, and you've hard-coded in the initial seed. So we had an initial seed of 15 for our music generator. Every time we run that code, the first one that's going to be played is Oliver's Army. It's going to get pretty boring after a while, okay, because it will be the same time every time, okay. So it would be better that we wrote a code that when you loaded the code, when you ran the code, it didn't have initial seed equals 15 hard-coded in. It could somehow randomly pick an initial seed. Okay, so how do you do that? If you could do that, the initial seed would be different every time. It means the first song you hear will be different every time, which would be grand. we'd still get bored because we only had 32 songs, so still after a while we'd begin to see the pattern. But for a very big random number generator, it's important to start off in a different place every time you run the code, because otherwise you're just going to get the same numbers every time. How would you do that? How can you produce a random number? I'm after saying that computers can produce random numbers, and now I'm saying we should do some random initialization of the seed. But one thing a lot of people do is they make the initial seed maybe taking the current value of the clock. So you ask MATLAB, you make a little temp variable, say temp is equal to clock, and that will make a little array in MATLAB with 6 elements. The 6 elements are the year, the month, the day, the hour, the minute, the second, 6 numbers. And then you can take the 6th such number, which is the second. That's obviously changing the whole time. And you can maybe round it. It's going to give you a number between 0 and 60. You can round it to some integer between 0 and 60, or 0 and 59, more precisely. And then you can scale that to give you any number you want. So this will initially give you a relatively random number. It's whatever time the program started at, between 0 and 59, and then you can scale that. So that's a good trick then. If you want to write a random number generator, but you don't want to always kick it off same way every time, you should do something like this. Okay, another problem, how to avoid overflow. This is less useful for you guys. It's useful if you're working on a very small device using integer arithmetic, maybe using a microcontroller or something, but if we're doing it in MATLAB, it's less of a big deal. But you've got to be just aware of the fact that if we implement this Parkin-Miller LCG on a 32-bit machine using integer arithmetic, we could run into trouble because when you do this multiplication, a multiplied by x, the resultant number could be up as far as 2 to the 45, and that's going to cause overflow because depending on your maximum value of your integer, this is going to be bigger than you can store, and it's going to get confused and give you rubbish numbers, okay? So unless your maximum int is greater than or equal to 2 to the 46 minus 1, you're going to run into trouble because occasionally you're going to produce numbers in the algorithm that cannot be stored as an integer on your device because your device is memory limited. Overflow will happen, you generate an error. So the other thing to do is to work in real arithmetic. So again, this is moot for us because we're going to be using MATLAB, and MATLAB will save everything as real numbers as appropriate. But it's just something to be aware of if you're ever doing it on a microcontroller or something like that. So generally, real arithmetic uses 47 bits, which is plenty big for the biggest number that's going to turn up in this particular calculator. Okay, put some more notes in that. Okay, so we talked about random number generators. We've seen how to make them. We've looked at how to make maximum period, make sure that the numbers move around a lot. There's no structure to it. There's no correlation. It isn't going odd, even, etc. Another important thing we've got to be able to check is that we are supposedly producing uniformly variable random numbers. So random numbers which are distributed over an interval, from say 0 to 1, and are uniformly distributed. Okay, so uniform distribution is characterized by several numbers, or indeed any probability density function is characterized by several numbers. One is the expected value, and one is the variance. So every probability function, such as a Gaussian or a Rayleigh or a uniform or anything like that, has these two numbers and has other numbers particularly useful. The expected value is sort of the number that occurs most often. It's the center of mass of the distribution. So for a Gaussian distribution, the expected value is generally 0. It's a normal distribution. Okay, so most often numbers are close to 0 and less often further away. So the expected value is 0. The variance tells you how much spread you get. Okay, so for a Gaussian distribution, the average is 0, but you can get big numbers. You can get big negative numbers. The variance tells you how likely those numbers are. It effectively gives you a measure of where the bulk of the numbers lie. Okay, it gives you a measure of the spread, how likely very big or very small numbers are. Okay, so we can work out that are the formulas. So for us, we're interested in uniform random variables. The uniform random variable has a probability density function given by f of x equals 1, provided that x is between 0 and 1. It has it's 0 otherwise. So we're assuming a uniform random variable where the random variable can only take values between 0 and 1. So within 0 and 1, they're all equally likely, and outside 0 and 1 can't happen. So this is what we're going to try and create with a random number generator. So in that case, the expected value is the integral from minus infinity to plus infinity of x times the density function integrated. Well, in this case, the density function can only exist between 0 and 1, so we change our limit to 0 and 1 because f of x is 0 outside of this interval. Within this interval, f of x is equal to 1, so we replace f of x here with 1, and we get the integral x dx from 0 to 1. That's x squared over 2, which gives us a half. Okay, so the expected value of a uniform random variable uniformly distributed from 0 to 1 is a half, slap bang in the middle. Okay, it's the center of mass of that distribution. The variance is obtained by doing this calculation here. We get x minus the expected value squared. So this is a measure of spread. We square it to make sure it's positive. We multiply it by the density function to weight it by the various densities or the various probabilities. Again, f of x only exists between 0 and 1, so we change the limits to 0 and 1. We get f of x is equal to 1 within that limit, so we replace it with 1. Here we get x minus a half squared. To do this integral, work it all out at the limit to get 1 over 12. Okay, I won't do it. It's an exercise for you guys. Go and convince yourself that will happen. Okay. Okay, so a good LCG generator is going to generate numbers between 0 and m minus 1. We can divide those numbers by m or m minus 1 to produce real numbers between 0 and 1. And what we would like to know, are those real numbers between 0 and 1, are they a good uniform distribution? Are they going to be a good uniform distribution? One thing we would like to know is that, well, if we were to sum the numbers or to take a sample of the numbers, would we get a sample average close to a half, which is the expected value for a uniform? Would we get a sample variance close to 1 over 12, which is the expected one for a uniform? Okay, so we need, these are necessary but not sufficient. So we could have a random number generator which looks like its full period, the numbers jump around a lot, but we need it to satisfy this condition as well. Okay. And you can show, here's a very trivial one, LCG 114096. And if you work out the average, this produces a sequence of numbers. You work out the average of these numbers, you get average of 0.4999, very close to a half, and variance 0.0833, very close to 1 over 12. So it matches this criterion, but it's a crap LCG because if you work it out, it just generates the sequence 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this condition here of matching the average and the variance is important, but you still need something which is random at the same time. You need both. So for LCG, this one here, 63131, we get an average of about 4872, a variance of 0.0812, close enough to a half, close enough to this, not too far off that. You get reasonably random looking numbers. The reason it departs from this is because there's only 13 numbers here. So when you divide the integers that come out by 13, it's a very sparsely populated real number line. You only get a very small number of the real numbers. Okay, because this is a discrete process. You don't get all the real numbers between 0 and 1 because you can't, there's an infinite number of them. But in this case, you're getting a very coarse resolution. So, but even despite that, we're getting something which has sample average and sample variance close to what we want. Okay, and we're finished. Slide 106. Good. Slide transition 106. Has anybody got any questions before we stop? You guys are probably knackered. I'm just going to go and sleep. Manuth, send me a text if you have any questions. You've all fallen asleep over there too, have you? Okay. Nobody's any questions. So what we'll do is we'll leave it there. Thanks very much for your attention. Check out the website. I'll be putting more notes up on the website, and hopefully I'll get a recording of this up on the server as well for the NUIM people. Hopefully you won't need it. I don't think the connections dropped out too much there this week. It seems better, but I'll put a recording up nonetheless, okay? Okay, talk to you next week. See you then. Bye.